to record you. Okay, this next talk is by Daniel Remenik, who will talk about non-intersecting Brownian motions and random matrices. Daniel.
Thanks, Paulo, and thanks to all the organizers for the invitation, and thanks to everybody who made it to the end of today's session of talks. So what I want to talk about today is something, well, really what I want to do is give you an overview of several different results about non-intersecting Brownian motions and some relations to random matrices, which I'm going to explain. So there's several co-authors here, so I'm gonna mention them as I go. But let me first start with describing the model. So the model is this, by now, very well-known model of non-intersecting Brownian motions. So what you do is, these are really Brownian bridges. So I take n Brownian bridges. So time goes from -1 to 1. All these bridges go from 0 to 0, and they are conditioned not to intersect. Okay, so you can do this conditioning in more than one way, but one simple way is simply to make them start and end at sort of distance epsilon, and then take epsilon to 0, and this works perfectly, and you get a picture like this one. So this is in the physics literature. These people call this the watermelon model, because of course it sort of looks like a watermelon. Okay, so these are non-intersecting Brownian motions, and there's the very first connection to random matrices is the following. So it turns out that if you fix t, actually more than this is true, but at least if you fix t, and you just look at the location of these Brownian motions, okay, you get a point process, and this point process is exactly given, well, modulo some scaling, which has to do with time. It's exactly given by the eigenvalues of an n times n Gaussian emission matrix. So a matrix from what's known as the Gaussian unitary ensemble. Okay, so you just fix this time, look at these points, and what you see is the eigenvalues of a GUE matrix. Actually, it's not only this that it's true. This is also true for all t in a sense. So actually, this model of non-intersecting Brownian motions is a random matrix model. In the following way, you can map this model to a different model, which is Dyson Brownian motion. And what this model is you simply take one of these matrices, one of these GUE matrices, and you let every entry run as a Brownian motion, and look at the eigenvalues. So the eigenvalues are going to be describing a set of non-intersecting paths. They're not going to intersect because with probability 1 at each time, at least, a GUE matrix doesn't have repeated eigenvalues, so they're non-intersecting. And what you see in the end is really the same picture as this one. Okay, you can map one to the other, and the way in which you map it is essentially given here. Okay, so these are non-intersecting Brownian motions. And a well-known fact is that, so what you want to do here is look at the top line. Actually, you can rescale everything, but I'm going to look at the top line, so the one over here. Okay, and you can check that due to this non-intersecting condition, the maximal height that this, that essentially here at the middle, that this watermelon attains is of order root n. Okay, so this is due to the non-intersection. And if you recenter and rescale with this 1/3 exponent here, so this is the famous random matrix or KPZ 1/3 exponents. So if you rescale in this way, and then fluctuations are going to be of this order, you take the limit, you get something that's called the Airy-2 process. So the Airy-2 process is just the scaling around sort of the center of this top path. Okay, so what is this Airy-2 process? So it's the one over here. It's a stationary process. It's not a Markov process anymore, but it's a stationary process, and the marginals are what's known as the Tracy-Widom GOE distribution. Okay, so it's just the asymptotic distribution of this top eigenvalue of the GOE matrix that I was mentioning before. So this is the Airy-2 process. Where does the Airy-2? So the Airy-2 process wasn't. So the Airy-2 process stands for two slightly different things, but in this context, this Airy-2 process, the one that arises here, comes from, or it was originally introduced in the context of last passage percolation. So I'm going to make some connections with last passage percolation. So I'm going to very briefly introduce it. So last passage percolation is the following model. I'm going to look at, so I have Z2, and then I put IID exponential weights on the vertices. And what I want to do is I want to look at paths which go from 0 from the origin to some point m comma n. And I want to look at the path, along the path, I sum these weights as I do here. And then I look at the path of maximal maximal sum. Okay, so this is the last passage path. And if I go from 0, 0 to mn, and then I look at this maximal last passage time, this is what's known as the point-to-point last passage time. And what, well, essentially Prahofer and Spahn showed in this model, it was first shown by Johansson around 20 years ago, is that if you look at the point-to-point last passage percolation times, so you go from here to here, but then you move along this anti-diagonal path in the right scaling, and now the right scaling is this scale of 2/3. Then, as you move this point along this anti-diagonal path, what you see is exactly the same ARI2 process. Okay, so it's the same process that arises from random matrices or from non-intersecting Brownian motions, comes here from last passage percolation. And the next ingredient that I had to add, so here in the previous slide, I was looking at point-to-point last passage time. So I start from a point and I go to a point, and then I can move the point to see some process. But now, suppose instead of going from a point, I just take paths which go from this anti-diagonal line at the beginning all the way up to this point NN. Okay, so this is called point-to-line last passage percolation, or line-to-point last passage percolation. But essentially, I'm looking at all possible upright paths which end at n comma n and they have to have length 2n. Okay. So it was shown in a slightly different context by Bike and Rains, also about 20 years ago, that if I look at the last passage time in the point-to-line case, then what I see is convergence to a Tracy-Widom GOE distribution. So this is, again, the asymptotic distribution of a certain random matrix model, of the largest eigenvalue in a random matrix model. But the difference is now that my matrix is symmetric and real instead of being complex and Hermitian. But anyway, the point of the story is that this quantity here comes from maximizing in this direction, okay? And everything is reversible. So in my previous slide, I was talking about this ARI2 process which appears here. Okay, now I'm moving around there, but essentially what I have just said tells me directly that if I compute the supremum of this ARI2 process minus a parabola, I haven't mentioned the parabola, but this is just an additional shift which you get, then you get this Tracy-Widom GOE distribution. Okay, so there's this variational formula relating the ARI2 process with the Tracy-Widom GOE distribution, which is sort of nice in a way because this one, as I was saying, has Tracy-Widom GUE marginals, but when you compute the sup in this way, you get this Tracy-Widom GOE distribution. So actually, this is just what this is really is showing you that this GOE distribution arises as the universal fluctuations of KPZ models with flat initial data. So what I'm doing here, you can think of KPZ models in the context that I'm only gonna look at a restricted setting, but essentially what I'm putting here is the initial data for my KPZ model in a certain way, okay? And then you can think of either as this last passage percolation model, or you can think of the interface of points which you can get to by as n grows, and then you would get some sort of growth model, and the initial condition would be exactly this one, okay? And growth is in this direction, so this is the flat initial condition, okay? And the way in which it shows up is here, okay? So as I was saying, it's the supremum of this ARI2 process minus a parabola, but I can also think of it as adding 0. And this is just what I'm trying to say here is that this is just an instance of a general fact that for any KPZ model, if you start with some general initial condition, so something like this red curve, and then you think of this as sort of converging to some limiting initial profile, H0, then the fluctuations of this KPZ model are going to be given in distribution as the supremum of the same area2 process minus a parabola plus this initial condition. Okay, so what I'm writing here on the left is really the KPZ fixed point with that initial data, but I don't want to get into that too deeply. Okay, so essentially you put here a function and then passing through this variational formula, and it gives you the asymptotic fluctuations of KPZ models with the chosen initial condition. Okay, so now I go back to my non-intersecting Brownian motions. So as I was saying, well, on the one hand, I told you that if I rescale around here in the right way, what I see in the limit is this area2 process minus a parabola. But on the other hand, the area2 process minus a parabola, the soup of that converges to GOE. So what that tells me, if you put in the scaling, it tells me that if I look at this maximal height, okay, so this is what's on the left-hand side of this convergence. I take this maximal height of my Brownian motions, I subtract the expected height, which is around √2n, and then the fluctuations are of this order n to the minus a sixth. So if I do this, what I get is convergence to this Tracy-Widom GOE distribution. Okay. So well, you have to do something to show that the limits commute, but this can be done. It essentially follows from a work of Corwin and Hammond. So now we get this, and this is sort of the starting point of the story I want to tell, is that there's these relationships between that you get from non-intersecting Brownian motions through variational formulas, and they give you some other random matrix quantities. So I'm essentially not going to talk about proofs at all in the talk. So I just want to tell you, the purpose of the talk is tell you about some related results to this one, okay, to the one that's circled on the top, okay, this convergence to of the maximal height. So I'm really not going to get into details, but let me at least tell you very roughly how one proves such a thing. So well, one proof is the proof that I just explained. So it comes from this computation at the level of last passage percolation, and then you put things together and you realize this. But there's actually a direct proof, okay? And the direct proof, well, this one uses exact formulas for the non-intersecting Brownian motions. The other one used essentially exact formulas for last passage percolation and this connection. And the proof is based on an exact formula of this sort, okay? So this is a formula that really works in a much more general setting. But in this setting, it tells you that if you want to compute the probability that the top path, okay, so my Bn is the one on the top, lies below some function g. So I fix some g here, and I want to know what's the probability that the function lies below there in some interval, say, ab. Okay, then what I have to do is I have to compute a Fredholm determinant, okay, whatever that is, but probably most of you have heard about it. It's just an infinite dimensional version of the determinant. There's something called the Hermite kernel in this case, which is something essentially coming from random matrices. But the important part is this operator p hit. I'm going to tell you what this operator p hit is. So what you do is the following thing. You have your function g up here, and then I go from a to b. And what I have to do is I'm going to run a Brownian motion from A to B, okay? And I just ask, what's the probability that starting from A, okay, let's say I start from X, I want to know what's the probability that at time after I get to B, I'm at Y, and that I have hit this function G. So it's essentially a hitting probability for a Brownian motion, okay? So this is what goes inside the formula. This is what you have to compute. And in the problem that I'm looking at here, I'm trying to compute just the distribution of the max. So essentially, I'm just computing the probability that this max is less than some level R, say. So these heating probabilities are very easy to compute. It's just the reflection principle for Brownian motion. And then you can start, then you can get started and try to compute things and in the end get formulas. So that's how you would prove this directly, okay? So what I was saying in the next piece of this slide is that this formula actually works in much more generality for many other processes, and it can be used to prove several other identities in the same way by getting formulas like this and computing these exact heating probabilities, putting them inside the determinant and trying to compare what you get. So that's what I want to tell you about. The same thing for in other cases. So I'm going to show you a couple of different results making connections for versions of the same problem. So now what I want to do is look at the same problem, the maximal. So let me go back just a little bit. Okay, so over here, sorry, over here I was looking at this maximal height, right? But I was taking a limit as n goes to infinity, rescaling and getting this limiting random matrix distribution. So a reasonable question is, well, what if I don't take a limit? What if I just fix n and try to study the distribution of that random variable, of that maximum? Okay, so that's what we did with GOE a couple of years ago. And the result is the following. So it turns out that it is true. If you look at this maximal height, the one over here, it is related itself without taking limits to a random matrix quantity. And the quantity is the following. It is really the largest eigenvalue. Well, there's a square here, but that doesn't really make much of a difference. It's the largest eigenvalue of another random matrix. And the random matrix is really just a real Wishart matrix. Okay. So you take a matrix, which is of size n plus 1 times n, and then compute x transpose times x. So this is just a sample covariance matrix if you want. Everything is real and Gaussian, and compute the eigenvalue of this. And that's the distribution you get on the right-hand side. Okay. So the proof of this uses essentially this idea that I was showing you before by explicit computations. And there's actually, last year, there's a paper by Fitzgerald and Warren, who they were doing something sort of related. But in particular, they gave an alternative proof of this based on something called RSK, for those of you who know what this is. But essentially, there's a proof which makes a connection with last passage percolation and gets the same result. Okay. Okay, so we have this connection with the largest eigenvalue of a finite random matrix. Oh, okay, and yeah, what I was saying here is that this eigenvalue, the distribution of this quantity actually converges to the Tracy-Widom distribution as n goes to infinity, so one recovers the previous result, the one that I was showing you at the beginning. Okay, so next thing I want to look at, just because it's in the spirit of exploring what else we can say. So now, instead of looking at the soup of my watermelon, if you want, over the whole interval -1 to 1, what I'm going to do is that I'm going to stop at time p, and I'm going to look at the soup over here. Okay, so that's that quantity that I'm circling there. Okay, I want to look at the soup, but on a half interval. Well, if you rescale in n, so that you go to this sort of ARI2 process limit, so you can do the scaling, and what you're going to get is that this supremum on this half interval, it also converges to the supremum on a half interval of an ARI process. Okay, so now it's the supremum. Instead of taking the supremum over all of R, I take the supremum over a half interval. Okay, and again, this is, you can think of this as the universal fluctuations of KPZ models, but instead of putting flat initial data, you put something called as half-flat initial data. So it's essentially flat on one side of these, on a half interval. And well, this is a problem that's sort of well studied, and you can guess what you're going to see as you move A in this case. So forgetting for a moment about this green thing, if I take a to infinity, so a is here, right? So if I take a to infinity, I'm recovering the supremum over the whole line. And then I should be converging to this Tracy-Widom GOE distribution, right? It's the same problem I was showing you before, supremum over the whole line. Now, it turns out that here what I should do, if I now want to look at what happens as a goes to minus infinity, well, you see, when a goes to minus infinity, this supremum is going to be attained, so the RE2 process is stationary, right? So really this RE2 process minus parabola looks like this. It essentially looks like a perturbation of a parabola, okay? So if I take the sup over an interval like this, the sup is going to be very near a, right? Which means that this is going to be essentially of order a squared. Sorry, minus a squared. Right. So I should add a squared to compensate. And it turns out that if you compute this limit now as a goes to minus infinity, you're only the supremum only sees this airy part, right? Because it's essentially you're computing the supremum is going to be exactly area of a, right? As a goes to minus infinity, because you can't go very far to the left because of this parabolic term. So as a goes to minus infinity, what you get is this Tracy-Widom GOE distribution, okay? Because that's the distribution of the marginals of the airy process. So this is what you see in the scaling limit. And well, the next question I wanted to present is, well, what happens if I do the same thing at the level of the Brownian motions, okay, before taking a limit? Okay, so I'm going, one has to choose the scaling carefully here. It's not very relevant. So again, I'm going to look at the supremum over this half interval of this, the top Brownian path, okay? It's squared just as it was squared before, but that's really not very important again. Now, let's forget about this green part again. As p goes to 1, I'm recovering the previous problem, the one where I compute the supremum of the whole top path, right? So I would expect that, and of course that's what happens, to go to the same distribution, to the same Laguerre orthogonal ensemble distribution, which is just the real Wishart matrix. Now, if I want to take p to minus 1, so it means that I'm looking very close to this point over here, just as I had to compensate here with this a squared, here I have to do something to compensate for the fact that these Brownian motions are getting they're getting squished near 0, right? And actually the right scale is this root of 1 plus p, because this is there's this macroscopic shape that my Brownian motions are going to be following, and it's an ellipse. So in this way of writing things, you get here a root of 1 plus p. And as p goes, the point being that this is going to 0 as p goes to minus 1, and I may be able to see something interesting. So the question is that, it's what do you see? And well, here is the answer. So the answer here is a little bit more complicated. So let me go back to these Wishart matrices over here. So in the case that I was showing you before, we had real Wishart matrices, right? Just matrices, sample covariance matrices for real Gaussian ensembles. Now, suppose instead of doing that, I take complex Gaussians. So again, now I have complex Gaussian samples, and I compute this sample covariance matrix. Well, that's known as okay, this is a type, of course, that's supposed to be the Laguerre unitary ensemble. And for all of these models that I have been talking about, you can compute the joint density of eigenvalues. So this is a classical thing in random matrix theory. And for this case, this is the joint density of eigenvalues. So if I compute a matrix like this M here, then the joint density is this product of lambda I to the A e to the minus lambda I times this, this is called the van der Monde determinant squared, which is what you always get in this sort of thing. And the important thing here is this A. So A is measuring how much wider my sample matrix is than taller, right? So it's X is of size n plus A times n, and this A here shows up in the joint distribution of the eigenvalues, okay? So, okay, this is the joint distribution of the eigenvalues, and I can sort of forget about the random matrix original story about this distribution, and I can think of this as just a distribution over n points in the real line, right? So now I have n points on the line which have this joint density, and this joint density is the one that corresponds to this complex Wishart matrix. So this is what's known in the literature as a Coulomb gas or a log gas, right? So this is just a general way of writing a joint density. Well, it turns out that this distribution that I was discussing, the limit as p goes to -1, which one would expect to have to do if the limit as p goes to 1 had to do with with real Wishart matrices, it's reasonable to believe, because of all the story that I've been telling you, that as p goes to -1, it should have to do something with complex Wishart matrices. And yes, it is, but sort of. So what you get is the largest eigenvalue, but it's not really an eigenvalue, or at least we don't know if it is an eigenvalue. It's just the largest point in this distribution, the one over here, but where A equals 1/2. So that's what you get. Okay, so this is essentially some sort of generalized Laguerre ensemble. Okay, and we don't know. It sort of belongs to the same class of distributions, but we don't know if it really comes from any random matrix distribution or not. Okay, it's just a distribution on endpoints. But again, one can check that this in the limit will go to the Tracy-Widom GOE distribution, so one recovers the original result. So I forgot to say, this last theorem is joint work with Yamit Yalanda, who's a PhD student of mine, and Nicolás Salduendo, who was a master student in Chile, and he's now a PhD student in Nancy. Okay, so time has gone faster than I thought, so I'm gonna very, very fast try to explain the last model that, I guess, Paulo, I have a couple of minutes left. Okay, 3. Okay, so, fine. I'm going to explain this very briefly then. So the last model I wanted to discuss, but it took longer to explain the other ones than I thought, is, so now I'm going to sort of change now I'm not going to look at half intervals. What I want to do is look at the same model, but now instead of having every Brownian motion go from 0 to 0, I'm going to pick, say, some Brownian motion. A given number. In this picture, I take 2 of them, okay, and I'm going to let them start from different points, not necessarily the origin. So this is known as non-intersecting Brownian motions with outliers, and here we would have 2 outliers, okay. And what I want to do is I want to scale this in an interesting way. If these beta 1, beta 2, alpha 1, and alpha 2 were sort of, I don't know, at some distance which is order 1, as I take n to infinity, I would not see anything in truth. So essentially, I would see the same scaling limits, because a difference of order 1 doesn't really make any difference. So what I want to do is put these starting points and ending points near this critical root 2n height. And the right way to do it is to scale it in this way. So you just sort of focus around root 2n, with this perturbation, which has to be of size n to the 1/3, okay, on the 2 sides. And okay, I'm gonna skip this. So what we want to study now is the maximal height of the top path, but with outliers, okay? And see if we can say something. Well, this is this is more recent, John. Well, the other work with my students is still actually in progress, but it's almost done. This is work from last year with Carl Lichty and Dawn Nguyen, where what we could do is compute this soup. Actually, it's the computing this is not a big deal. And again, you get a Freedom determinant formula. Okay, and it's with the same sort of methods. So since I don't have time, let me say that I want to show something that comes here in the rest of the slide, but there's a connection between this and again random matrices, but in a strange way. So what we can do, and I won't get to that, we can show that this distribution as a function of R solves a certain equation, which is it's a PDE which arises again for the scaling limit of complex Wishart matrices. Sorry, not really complex Wishart matrices. Let me just say Wishart matrices. So it solves a PDE, which again is related to Wishart matrices in a way which is not completely concrete. Okay, so I'm sorry because I won't get to that. I want to show just something that I find very curious, and it is the following fact, okay, which follows from this formula. So just by looking at this formula, you discover something which I still find quite surprising in a way. I mean, it's not such a big deal, but it's surprising. And what's surprising here is that this formula is completely symmetric in the starting points and the ending points. Okay, so it means the following, and I'm going to draw a picture, explain it, and then I'm going to be done. So if you do this, okay, so I have here my that's supposed to be my watermelon, and if I put, say, two, sorry, so let me just draw the following thing. So suppose I take two outliers like this, but the outliers now I make them start at 0 and end at, say, A and B. Okay, and I compute the supremum of this path. Well, what this tells me is that in the limit, it is the same thing as the following. Instead of having two outliers, now I'm going to have just one outlier, but the outlier is going to start at B, say, and end at A. And now I compute this sup. The scaling limit, the supremum, the maximal height of this is the same as the maximal height of that. And it just shows up from the formulas. This can be seen, and it's not obvious, but it can be seen from a very special symmetry in last passage percolation. But if you look at this non-intersecting Brownian motion model, it's really not very apparent at all. Okay, so I'm going to stop here, and thanks for your attention.
Thank you very much, Daniel. Nice talk. So, is there any question or comment? Okay, so while the audience thinks about questions, let me ask you something that is bothering me since 20 years ago when I learned first this connection between last passage percolation and random matrices. Is there any, besides the computation that gives you this result, is there any intuition why one thing should be connected to the other, or either in any of those results here?
Yes, I guess yes and no. Basically, so okay, there's two ways of seeing it. So you can see, if you want this result I was showing, the result about this, sorry, this result, if you want. This is not giving you an explanation, but this is an instance of the fact that this right-hand side can also, it also appears in last passage percolation models. So These, even though the original results were for scaling limits, and you can believe that maybe in scaling limits you can have some coincidence because I don't know, many things go to a Gaussian distribution if you want, and they don't really have to share something. Results such as these tell you that no, really there's relations at the microscopic level somehow. So now maybe to answer your question a little bit better, there are models which give you couplings between random matrix objects and last passage percolation objects. Or maybe it's a little bit easier to state at the level, so the very good couplings, or at least the ones that I would consider most more informative, are they relate models which are of random matrix type with particle systems like TASEP. So you can actually build a model where you have a bigger model. It's really a model on triangular arrays of particles. And on one side of the array, you would see, say, TASEP. And on another side of the array, you would see something like non-intersecting Brownian motion, which is a random matrix model. Now, but the thing that I have to say is that that only works for essentially one choice of initial condition for TASEP, if you want, which at the level of last passage percolation means that this only works for point-to-point last passage percolation. For something like point-to-line, which is essentially what I'm doing here, the relation is more tangential. So it's like there's two worlds, and they have a little intersection, which you can try to probe and understand. But then they seem to each go, in different ways.
Okay. So okay, then you send me some reference for these couplings. I would like to know much more about.
Sure. Yes.
Yes. Okay. So is there any other question? Okay. Let's thank Daniela and the rest of the speakers for this nice session.